Hello and welcome to the lesson 24, and we're looking at hypergeometric distributions. So we are at the last of our types of distributions. We've talked about uniform distribution, binomial, geometric, and now our last one's hypergeometric. So what's today's goal? Very, very similar to previous days. You need to be able to identify when it's a hypergeometric distribution and then successfully apply it to the situation at hand. All right, so moving through it. Hypergeometric distribution. It's a fancy way of saying random selections without replacement. So this is the situation where you draw a card from a deck and do not put it back in the deck. You then pull another card. So the probability is not the same each time. So the experiments then are not identical. They're changing and they are not independent. So every time I pull a card from a deck and don't put it back, that deck is now smaller. So hypergeometric is the distribution that deals with a changing situation. So the formula, I'm going to show you how it's developed, and then at the end of it, you just need to understand or have that formula written down because all the concepts are there for us. So simple probability, so I'm going to go way back to Unit 1. So remember our probability, we were writing it like this back in the Unit 1. Where n of a is the number of ways you can have success over the total number of outcomes. So we're now our total number of outcomes, n of s. So my focus to start with, I'm just going to look at this denominator. We're going to change this formula or make it into a hybrid version of what the original one is. It's now split into two categories, success or failure. So we're still looking at the situation we're either going to have a success or we're going to have a failure with hypergeometric. The difference is, if it's a success or failure, we're still keeping that card. We're keeping keeping it out of it to affect the next shot. So what that means is that our denominator now will become our n of s, total number of outcomes, is equal to a successes plus b failures, and from that we are going to pull n of them. Okay, so n is the number that we're interested in. Now, for the people who are using the other form, it looks like this, a plus b combination n. Okay, so where a is number of successes, and when I do an example, this will make a little bit more sense. Is number of failures. So really there's only two possible outcomes here. You're either going to have a success or a failure. So if you're looking to draw the jack of spades, if it's not the jack of spades, it's a failure. And n is the number of trials. So how many times are you going to do? How many cards are you going to pull from the deck? All right, so that's part of it. So now we have the denominator figured out. So we know what the denominator of the hypergeometric formula is going to look like. Okay, so the number of x successes results, x successful results, they have to be taken out of pool A. So pool A is all the successful possible outcomes. So we're going to look at part of the numerator to look like this. There are, and remember a committee question, hypergeometric is very similar to the committee question in the respect that there are A females or A number of males, whatever we're looking for, and we're going to pull x of them out. Okay, so we want, out of the A, this is how many successes I want. Okay, so off the side where x is our number of successes. So do we want 3 spades? Do we want 3 females? Depends on the situation. The number of failures then is n minus x. So remember, and I should have that, sorry, I should have that other notation for people that are using the combination notation. So let's see if I can not do that. And maybe I'll write it in here, a combination x. Okay, there are a number of failures. There are b failures in total to pull from, and this is how many failures occurred. The number of trials minus the number of desired successes, and this is the same as saying b combination n minus x. So same notation. Okay, so our final formula then, going back to the original one that I talked about, everything always stems back to this formula here, basic probability. It now looks like this. Because it's a distribution, we're talking about the new notation. So random variable equals particular value. And that formula will be the A, choose X, so that's the number of successes I'm looking for, B, n minus X, divided by A plus B, n. And I'll change that also because I know a lot of people prefer the other form as well. So A combination X multiplied by B combination n minus X, all divided by A plus B combination n. All right. So there is the formula, and you just need to write down the one version. I'm not going to ask you to have both versions, so the one version that applies to you. And this will take care of a hypergeometric distribution, and it looks strangely like forming a committee question. Okay, and the expected value formula. Expected value is still the EX. So expected value. And it is going to be following my notation here. Total number of trials for whatever you're doing multiplied by the number of successes divided by total number of successes and failures together, or successful items together. So there's your expected value. All right, so let's take a look at an example. Three-part question. A drawer contains 5 red and 10 blue socks. So just summarizing here, 5 red, 10 blue. 3 socks are picked. So we are going to actually draw 3 socks out. So this is our X. Okay, no matter what the question is, we are pulling 3 socks out. Determine the probability that. So A part. You choose a pair of red socks. Well, if I'm pulling out 3 red socks, or sorry, 3 socks in general, and I'm looking for a pair of red, I can end up with probability that I have 2 red, or if I pull out 3 red, it'll also give me a pair. So I'm doing 3 draws regardless, and I could pull out 2 red, I could pull out 3 red. So let's identify some of the information here. So based on the formula I gave you, A is the number of items that will provide you with success. So we are looking at red socks. So there are 5 successful items in this drawer, which means there are 10 items I would deem as failures. We don't want them. We've already identified X, in this case, will equal 3. And now the n value, the n is the total amount that we are going to select. And I've made a slight error here. I apologize. N is going to be 3 because it's the total number of draws. X is what we're looking for. X is the independent variable. Right here. There's an X value. There's an X value. So I apologize for the confusion here. N equals 3, and then X will equal 2 and 3, depending on where we are in the formula. So, running through the formula that we just had on the previous page, for an X value of 2, again, A is 5 successes, and we're looking at pulling out 2 red socks, which means that out of the 10 blue, I pulled 1 of them. In the drawer itself, there are a total of 15 items, and for this example, I'll do the 5 plus 10, and we're going to pull 3 socks out. So it is it's a committee question, no matter how you look at it. So committee question plus, now our second situation, what happens when I pull all red socks? Well, there were 5 red socks, and I pulled 3 of them. There were 10 blue, I pulled none. And in the denominator, there was still the 5 plus 10 or 15. You don't have to do that addition. And we end up with that. So, calculating it out. So just running to the calculator now. The 5, choose 2. And if you want to grab your calculator and give that a try, I'll give you a second. Okay, so using my calculator, I have the first fraction equal to 0.22, the second one equal to 0.022, which means that I have a 0.242. So therefore, probability to choose a pair of red socks is 24.2%. And again, we have to use this because when you pull one sock out, you're not putting it back in. You're going to keep it out. Okay, not many people pull a sock out, put it back in, pull another one out, and say, oh, I got a pair, because you only have one in your hand. So it's important that you actually pull two out of the bag. Okay, moving along then, if we look at B part, choose blue socks instead. So we want to do a pair of blue socks. So with B part, what changes? What changes? Well, off to the side here, my successes, there are now 10 blue socks in the drawer. For a success, that means now red socks are failure. So my A and B switch. N is still 3. I'm still doing 3 draws. And my X value is going to be still 2 and 3. All right. So same setup then. If I'm looking for a pair of blue, it would be the probability that I pull 2 blue plus the probability I pull 3 blue. So therefore I would have 10 successful chances, and I want to pull 2 on the first try. 5 red socks, which are failures. I'm going to pull one of those. So 15, choose 3. Plus, in the case that I pull 3 blue socks, I had 10 to pick, pull 3, 5, and 0. And in the bottom are denominators, 15, 3. And for people that are still thinking this is just a committee question, you're absolutely right. Okay, it is a committee question. That's what hypergeometric is. You're pulling people out of the group. So let's calculate that and see what it gives us. I'm finishing up this example, so I did the calculations. That's what each fraction respectively would give me. Adding those together, I get 0.759. So therefore, probability of pulling a pair of blue socks is 75.9 or 76%. Okay, finishing this question off quickly here. What's the probability you choose a matching pair? Okay, so C part, it would be probability of X equals a pair. Well, that would be the probability that I pulled 2 red plus probability I pulled 3 red. Or I could have had blue socks, probability of X being 2 blue. Or what happens if I pulled all 3 blue? Well, we've done all the calculations above. We know that this particular answer from above was 24.2%. Plus, we know the answer we just did in B part was 75.9%. If I add those together, 75.9 plus 24.2, I get 100%, off by a little bit. Well, that makes sense, right? It makes absolute sense. If you're going to pull 3 socks, you got to pull 2 of the same color when there's only two. So there's a 100% chance, right? And that makes sense. If you're pulling 3 socks, you have to pull 2 of the same color, so you're going to end up with a pair regardless. All right, so there we go.